Hello and welcome back to the Maths Behind Economics YouTube channel. This is video 7 and we will be talking about exponents and roots. However, there are quite some groundwork that we need to lay down, so I've decided to split the video into two parts. Our final goal is to show why the identity of nth root of a to the m is equal to a to the n over nth power. So basically, the connection between roots and fractional powers, but first we will need to understand properly how roots work. So first we will talk about the square root, then I'm going to introduce the concept of the nth root, and then we will talk about negative numbers under the root. With this we will lay the groundwork which we will be using in the next video when we will fully cover the identity. So let's get started. First we will discuss what square roots are. And we will start it through by examples. So square root of 4. Well, the basic idea here is we need to think about what is the number that needs to multiply by itself twice to get to 4. Well, we know that 2 times 2 makes 4, so the square root of 4 is going to be 2. Now, we have to be careful because negative 2 times negative 2 also makes 4. But when it comes to the roots, we only look at the positive numbers. One more thing, sometimes the square root is represented by this, but sometimes the square root is represented by this, which means that the number is missing from the sign of the root. Now the square root is the smallest root, that's why leaving the number out from the square root sign is quite common. Okay, let's look at something else. What's the square root of 9? Well, we know that 3 times 3 makes 9, so the square root of 9 is going to be 2. Well, in general, the square root is basically square root of a is going to be equal to some number, let's say x, when raising that x to the second power will yield a, the number under the root. Okay, so that's the basic idea behind the square root, which is the smallest possible root. Now let's up our game and let's talk about the nth root. And I'm going to make a bit more space. So what could be nth root? Well, we can talk about cube root of 27. Well, with the square root, we're talking about numbers multiplied by itself twice to yield the number under the root. With the cube root, we're just going to extend that to numbers multiplied by itself 3 times to yield the number under the root. So 27, what could that be? Well, we know that 3 times 3 times 3 makes 27. So that's going to be our cube root of 27. Well, how about cube root of 8? Well, 8 is equal to 2 times 2 times 2, so the cube root of 8 is going to be 2. How about the fourth root? Fourth root of 16. Well, I know that 16 is equal to 2 times 2 times 2 times 2, or 2 to the 4. Therefore, the fourth root of 16 is going to have to be equal to 2. How about the fifth root of 25? Well, now I'm in a little bit of trouble because 1 to the 5th is 1. 2 to the 5th is already 32. So the result for this is somewhere, so my x is going to be somewhere between 1 and 2, but I don't know exactly because this is not an exact number. 25 is not an exact fifth power of a number. So now I'm going to have to enlist the help of the calculator. So you pick up your scientific calculator and it has got a button which you can use for finding any root. So you have to give it which root, in our case is the fifth root, and what number you want to take the fifth root of. So I'm typing in 25 and 5 for the root, and then hit enter, and you've got a long number with many digits. Now, even that number is just an approximation because your calculator approximates to a certain set of digits. But what I'm going to do, I'm just going to approximate it to 3 decimal places. So that's going to be 1.904, because the next digit on the calculator would be 6, so therefore I would need to round it up. So not every root will be an exact whole number. As a matter of fact, you will have more of these type of solutions, more approximations, more decimal answers to these rules than whole numbers. Okay, so let's try to look at what does the concept look like in general. So with the square root, we used the letters a and x. Let's stick with that. So the nth root of any number is going to be a number x when that x number raised to the nth power will yield back a for us. Okay, so that's the concept of the roots, the square root and the nth root, which is basically whatever root in general. Now, so far we only looked at positive numbers under the root, but now let's play around with the idea of, can we have negative numbers under the root? So negatives under the root. Okay, I'm gonna make a bit more space again. And then let's play around with numbers. So how about square root of negative 4? Remember what was the square root? I need to multiply the same number twice to get negative 4. So negative 4. I know that 2 times 2 makes 4. So 2 times negative 2 would make negative 4. Or I could say negative 2 times 2. That would also make 4. However, 2 and negative 2 are not the same numbers. So I cannot multiply the same number by itself twice to get a negative solution. So in this case, it's not defined. We cannot have numbers multiplied by itself twice to yield negative. Well, not in the real numbers anyway. And when I mean real numbers, what I mean by is all the numbers that can possibly be represented on the number line. So every single point on the number line represents one specific real number. Now, what happens if I want to talk about the fourth root of a negative number? Let's say fourth root of negative 16. Well, I'm facing the same problem again, because as soon as I multiply negative numbers an even number of times, for example, I would have negative 2 times negative 2 times negative 2 times negative 2, that yields me positive 16, because these two cancels to positive and these two again cancels to positive. So if I want to end up with negative 16, I either have to have one of the numbers negative and all of the rest of them positive, or, and again I go a bit further up, or I have to have 3 of the numbers negative and 1 positive in whichever order that I want. However, in this case, I'm not multiplying the same number by itself 4 times, because in the first case I have got 1 negative 2, and in the second case I have got 1 positive 2, so it's not all the same numbers. So again, it's not defined. Now, how about the cube root of negative 8? Well, now I'm more in luck, because negative 8 is just basically negative 2 times negative 2 times negative 2. So I'm multiplying the same number by itself 3 times, so that is a possibility. How about the fifth root of negative 32? Again, same logic. Negative 32 is negative 2 times negative 2 times negative 2 times negative 2 and one more times negative 2. So 1, 2, 3, 4, 5 negative 2's multiplied together makes a negative 32. Again, every 2 of them cancels out to a positive, but I end up with one last negative, so that keeps the sign to be negative. So that gives me negative 2. Now, why is it important for me? Well, it's important for me because if I have got a negative under the root, whether it's defined or not will depend on whether the root itself is odd or even. Now let us make a bit more space and try to think about how we can capture what odd or even means. So let's talk about even or odd numbers. So how can we capture evenness? Well, even numbers are the numbers that can be divided by 2. Or I can also think about it, numbers that are multiples of 2. So an even number will be a number that is twice another number, where this new number k is a whole number. And what I mean by a whole number, we often use this funky double-legged z for whole numbers. Sometimes we also call them integers. But what's important that these are numbers like -5, -17, -38 through 0, and then all the counting numbers like 1, 2, 3, 4 all the way. So basically the easiest way to capture it's something like, I don't know, you start from some negative numbers and then you go from kind of -3, -2, -1 to 0, 1, 2, 3, and you carry on. So these will be all your whole numbers. Now, how about the odd numbers? Well, what does it mean to be odd number? It means that you can't divide it by 2, or it's not a multiple of 2, but you can also think about it slightly differently because every odd number is one bigger than an even number. So if you think about it, 3 is one bigger than 2, 5 is one bigger than 4. So to capture in mathematics, we very often use the notation of 2k plus 1. And again, here, this k is another whole number. So why was this important for me? Because I want to give you the formal generic definition of the roots. So again, make a bit more space. Okay, so let n be 2k, where k is a positive whole number, and let a be a number that is not negative, so it can be either 0 or positive. Then nth root of a is going to be equal to x when x raised to the nth power will give me back the a. Okay, so the nth root is basically a number that if I raise that number back to the nth power, I will get back the number that's under the root. So be careful because with an even power, I can only have non-negative numbers under the root. Now, what happens if I have got an odd power? So let n be equals 2k plus 1. And again, k is a positive whole number. Then nth root of a is going to be equal to x when, again, x to the n will give me back a. Now let's focus on the difference between the two definitions. So first of all, when we talk about an even root, we need the criteria for the number under the root to be non-negative, so it can be 0 or positive. But when we talk about the odd roots, that criteria is not necessary because negative numbers multiplied together odd number of times will yield negative numbers. So then the definition will hold for negative numbers in the case of odd powers, not in the case of even powers, right? I hope that you were able to follow through the logic and the thinking for this video. And now we laid the groundwork so we can move on to the identity between the fractional powers and the roots in the next video. See you then. Bye.